This is the third lecture of this week, and today's topic is conformal mapping. You see, the mapping is essentially a transformation or a function, okay, with sometime with special features. For instance, suppose if we write a function like this, suppose if we write a function f x is equal to f x y is equal to x square plus y square. So, this is essentially a mapping from one space to another space, mapping transformation from one space to another space. For instance, in complex variable approach, suppose if this is a complex plane, and if we have any point z, and if we have a function f z, and if we know the function is equal to u plus I v, that is how we can write a complex function. And suppose this space is u and v. So, corresponding, if this is S and corresponding say this is say f z. So, this is a map, this is a transformation, this is called a transformation, sometime which is also written as, or will be suppose w is a transformation, this is the w. Okay. So, this is a mapping, and then it is just not the mapping, it is conformal mapping, means there is certain properties need to be satisfied during this mapping, and that is what we are going to discuss today. Okay. Now, you see, suppose consider two plane, one is a complex plane x y plane or the z plane, and another one is the function plane u v plane. Now, you take any curve, for instance, if we take any curve, say this is any curve, say C in z plane, in the complex plane. Okay. Now, so if we recall, we can write, we know that z is equal to x plus I y, and then any curve can be written as say gamma s, which is x of s plus I of y of s. That is how we can. So, s is essentially greater than a to b. So, s is the so at any particular value of s, we can find out, we have the z is a function of s. So, at if this curve is defined between z 1 to z 2. So, z 1 is essentially your z 1 is gamma at x s is equal to a, and z 2 is equal to gamma at s is equal to, that is how we discussed in the previous class, right. So, suppose on a complex plane C is a curve, and then which can be parameterized, which can be parametric definition of that curve is this. Okay. Now, and then suppose on the transformation on this, and suppose this you have a function defined as this. You have a function w defined as f of z, and suppose this f is analytic function on this curve, okay, and also f dash z f dash, okay, we will come to this point. So, suppose f z is a transformation from x y plane to y u v plane. Then, if we have a curve C, then corresponding transformation on u v plane is, suppose that transformation is, suppose this is the curve we have, suppose this is gamma. So, essentially gamma is the transformation of curve C through this transformation, and this transformation is w. Okay. Now, suppose now consider a point here, point say at point on C, suppose this point is z 0, where z 0 is equal to essentially gamma at s 0. Okay. So, suppose at z 0 gamma z, this function is analytic function, we have already defined what is the definition of analytic function, and also suppose f dash z 0 not equal to 0. This means f dash gamma of s 0 that is not equal to 0. So, we have two properties. One is this function is z, this function is analytic at z0, and also that the derivative of this function is not equal to 0 at this point at z0. Okay. Now, if it is, then what we have? Then can we write like this? Suppose w is equal to f of z, and then with using the parametric definition of z, we can write that w s is equal to f of, then z can be written as gamma of s. Okay. Now, if we differentiate both sides, then what we have? We have dash s, that is equal to f dash, which is of gamma s, and then gamma dash s. Okay. So, this is the derivative that we also use in the previous class. Okay. Now, this is the derivative. Now, you see, since we have two conditions. One is this derivative exists, because when we say it is an analytic function, then this derivative exists, and another thing is this derivative is not 0. This derivative is not 0. See, these two conditions is important. Okay. If these two conditions are satisfied, what we are going to exactly do is, if two conditions are satisfied, then what happens if we have a curve C in xy plane, then if it is transformed through this mapping w is equal to f z, then what happens between these two between these two curves in this transformation? What happens? That is we are going to find out. Okay. So, now if we take, once we have this expression, now if we take argument both side, then what we have? Argument of, now both all are essentially the complex variables, right. Argument of w dash s, that is equal to argument of f dash of gamma s plus argument of gamma dash s. Okay. Now, let us see what these three arguments, this and this and this, they physically signify. Now, if we suppose draw a tangent at this point, suppose if we draw a tangent which is at, then this, suppose this angle is theta 0. Similarly, suppose the corresponding transformation of this point z0 is equal to this, which is say w 0, and similarly draw a tangent at this point. If we draw a tangent at this is the tangent at this point, and then corresponding angle say equal to phi 0. Okay. Now, this is gamma s, this is, let us use, this is gamma s, and then this tangent is actually your gamma dash s. Okay, this one. So, argument of this will be what? This will be theta 0, right. So, this will be theta 0, this will be theta 0. Now, similarly, now you see this is w, transformation of this curve, and its derivative is w dash is essentially, this one is the w dash, and its argument is equal to this angle phi 0. So, essentially this will be phi 0. Suppose this is equal to psi 0. Now, then from this equation, what we have? From this equation we have phi 0 is equal to psi 0 plus theta 0. This is important. Okay. So, what we have now on this slide is this. Now, if we have a curve defined on a complex plane, say curve C, and its projection or the transformation is gamma, and if we take a point on this curve, say z0 in this case, and at z0 if this transformation, this f z, that is analytic function, and also the derivative of that transformation is not 0, these two conditions satisfied, then this is the relation we have, and this relation tells you that Now, essentially, if we have to find out what is the physical interpretation of psi 0, see theta 0 is the angle of, if we have a slope here and this is the corresponding angle, and phi 0 is the slope at the project on this plane, and this is the corresponding angle, and essentially psi 0, which is equal to psi 0 is equal to phi 0 minus theta 0, it is the change in the rotation of this slope. The slope we have, and how the slope changes is orientation, how it rotates. Phi 0 is a psi 0 is essentially the measure of that. But okay, so this is the things, this is the equation that we have from this figure, right. Now, consider now we have one more curve defined on xy plane, or this complex plane, but passing through the same point z 0, and then look and we consider the transformation of that curve through the same transformation. And if we do that, suppose what we have is, we have two curve. In this case, it is, say this is C1, this curve is say C1, and this curve is say C2, and corresponding this is gamma 1 and this is gamma 2. And we have a transformation, this transformation from this to this is equal to W is equal to f of z, okay. And this point is z 0, this point is z 0 and corresponding point is W 0. So, W 0 is essentially the map of z 0, okay. Now, then similar to the previous slide, let us draw two slopes here. First slope is this one, this is drawn on C1, and draw another slope on, suppose then this angle is theta 1, okay. And similarly, you draw a corresponding slope here, and then this angle is phi 1. This is how we define, recall theta 0 and phi 0. Now, then we have two curves now. Now, draw another slope on this curve. Suppose this angle is, use different color just so that we can understand this. Now, this angle is suppose theta 2, and then draw another tangent here, and corresponding this angle is theta phi 2, okay. Now, then what is the relation between theta 1 and phi 1 and theta 2 and phi 2? Recall the relation between these are that phi 2 is equal to psi 0, 0 means psi was the argument of, if you recall, psi was the argument of f dash gamma s 0 at this point, since this point is same for both the curves. So, here also it will remain psi 0 plus theta 2. Similarly, we have phi 1 is equal to psi 0 plus theta 1. So, this is the relation, how this is the relation through which theta 1 phi 1 and theta 2 phi 2 are related. Please note that here this point z 0 is common, both the cases, both the curve point z 0 is common, and at point z 0 the function is analytic and the derivative is not 0, and psi 0 is equal to the argument of this at s is equal to s 0 or z 0. Okay. And since this point is same, your both the cases psi 0 will remain same. Now, from these two, what expression then we can write? We can write that theta 2 minus theta 1, theta 2 minus theta 1 is equal to phi 2 minus phi 1. This is important. Now, what it tells you? What is theta 2 minus theta 1? Theta 2 minus theta 1 is essentially the angle between these two slope. This is theta 2 minus theta 1, right? Theta 2 minus theta 1. Similarly, phi 2 minus phi 1 is this, phi 2 minus phi 1. This is phi 2 minus phi 1. Okay. So, what it tells you that if you take a point, or if you define first a transformation, say W is equal to f z from xy plane to uv plane, and then suppose that transformation is that function is analytic function, and at that particular point it is not 0, and then if you take two curves passing at the same point z0, and then the slope between the angle between these two slopes, which is theta 2 minus theta 1, and then if you transform this curve, if you project this curve on UV plane and their angle between two slopes is phi 2 minus phi 1, then these two angle remain same. So, as I at the beginning I said the mapping is essentially a function, sometime with some special features. Here it is a function, it is an analytic function, but with the special features that the angle between slopes at a given point, at this point where the function is analytic, the angle between the slopes remain same, they preserve. That is the special features we have here, and that is the reason why this mapping is called conformal mapping. The angle between these 2 points are preserved. Now, probably this thing will be clear if we demonstrate this through an example, but before that please note the two conditions, that the function needs to be analytic at that particular point, and then the derivative of that function should not be 0. Now, if we say, if we find out, if we suppose if you have a domain D here, in this case suppose if we define a domain, D and then its corresponding transformation is this. Now, if the function is this transformation, say f z, and if this function is analytic everywhere in this domain and everywhere the derivative of this is not 0, then this entire mapping is called the conformal mapping. So, if at every points that the condition that we satisfy, condition that we derived, the angle preserving condition, if that every point that condition satisfied, then we say that the entire map is the conformal mapping. Let us find out, let us give an example. Okay. Suppose consider a function f z is equal to, say f z is equal to, say x square minus y square plus I to x y. Okay. Suppose this is the map, between x y plane and UV plane. Now, from this, if you recall that we can write any function as u plus I v. So, this gives us u is equal to x square minus y square and v is equal to 2 x y, right. So, for this transformation, this is this. So, it says that if you take x y plane and then u v plane, you know the x y, you substitute x y here, you get corresponding u v and then you get the corresponding point. This is the transformation f z. Okay. Now, we will check whether the transformation is analytic, whether this mapping is conformal mapping and not. Just we take two slopes, two curves, and then find out the slope between these two curves in the x y plane, and then see what happens to the slope when it is transformed to projected onto u v plane, and then see whether these angles are preserved or not. Okay. Now, let us draw this. Let us draw in x y plane. Suppose this is the x y plane. This is x and this is y plane. Okay. Now, the condition is check whether let us first complete the problem statement. The function is given. Now, check whether the function is analytic or it is a conformal map at z is equal to I plus 1. At z is equal to I plus 1. This is the question. Okay. So, we have to check in the previous example, this z0 is essentially now we have I plus 1. Okay. Now, so let us take this at I plus 1, suppose this point is I plus 1, okay, means x is equal to 1 and y is equal to 1, and then take two curves. Suppose these two curves are, one curve is say C1, this is C1, and say another curve is passing through the same point. Suppose this is a straight line, this is C2. Okay. So, C1 is essentially your x is equal to y x is equal to y, this curve, and C 2 is essentially x is equal to 1. Suppose we have two curves. Okay. Now, we know that this angle between these two curves is, this angle is pi by 4, right. Now, next what we do, and this point is I plus 1, now, or 1 plus I. Now, what we do is, now let us see when these two curves C 1 and C 2 transform through this transformation, through this mapping. So, draw the corresponding space, say u v space, right. This is u and this is v. Okay. Now, you see what happens to C 1 curve. C 1 is essentially x is equal to y. Now, if we substitute x is equal to y, then what will be gamma 1? Gamma 1 will be if you substitute x is equal to y. So, for gamma 1 u will be 0 and v will be 2 y square. If we substitute x is equal to 1. Similarly, gamma 2 will be, if we substitute x is equal to 1, it will be 1 minus y square, u will be 1 minus y square, and v will be, if we substitute that, this will be 2 y. Now, if we combine these two, this u and v, then essentially this gives you an equation v square is equal to you can check it minus 4 into u minus 1. So, what happens when C 1, this curve is mapped, transformed through this transformation, then it becomes gamma 1, and in this case gamma 1 is u is equal to 0 and v is equal to 2 y square, means your gamma 1 becomes a line like this, like this becomes gamma 1. And then C 2, which was a straight line with x is equal to 1, and when it is transformed to the same map, then this becomes an parabola with this u v, the relation between the equation of that parabola is this in terms of u and v. And if we draw that parabola, then this parabola would be something like this. Okay, something like this. So, this is your gamma 2. Okay. Now, what will be this point? This point will be, we can check, this point will be when v is equal to 0, then u is equal to 1. So, this point will be 1, this point will be 1, and if you check compute that u is equal to, if you substitute u is equal to 0 here, then this point will be 2 I. Okay. So, essentially in this curve, at this point u will be 1 and v will be 0, at this point u will be 0 and v will be 2. So, this is the map of C 2, okay. And this is the angle they have, this is the angle we have here. Now, if we draw a tangent at this point, this is the angle between these two curves. Okay. Now, we have seen when before the transformation in xy plane, this angle is angle was pi by 4. Now, let us see whether this angle is pi by 4 or not. Okay. Now, remember if this transformation, this map, this function is an analytic function at the given point, in this case the given point is I plus 1, and this function is not 0, the derivative of this function is not 0 at I plus 1, then the angle preserved. What we do here is we will see that whether the angle preserved or not, not assuming, you can prove it, that I leave it to you. You can prove that whether this function is analytic at I plus 1 or not, and then check whether the derivative of this function is not 0 at I plus 1 or not. If that is done, then the angle preserve, and that is the part that we are going to show, the angle preserves. Okay. Now, let us find out how to find out the angle. Now, we have let us find out the slope of this curve, this gamma 2. Gamma 1 is very straightforward, this is just a vertical line. Now, let us find out what is the slope of gamma 2. Slope of gamma 2, in order to find out, we have to find out del v du, right. Now, if you if you see that the dV du will be in this is equal to minus 2 by V. Okay. Now, look at this point, we want to compute this slope at this point. Now, at this point just now we discussed V is equal to, at V is equal to 2 and at this point u is equal to 1. So, if you substitute V is equal to 2 here, then at this point your dV du will be minus 2 by 2 is equal to minus 1. Okay. Then what would be the angle between these two? This is a vertical line and this is the tan, this becomes minus 1, the tan theta become minus 1. Okay. Then what happens, this angle is also, this angle is also pi by 4. You can just with this figure. So, you see, so this is a conformal mapping where these two angles, if you take any arbitrary, this is just for demonstration, we have taken two angles, two lines, so that two very simple lines, so that we know the angle. But if you can take any arbitrary slope, any arbitrary points, and if at that point the function is analytic and derivative is not 0, then you can show very similar way that the angles are preserved. You can not show, we have already shown, we have already proved it. You can check with any example. For instance, in this example, if you take, you can see the angle is preserved. Now, that exercise I have done for you, and let us see how it looks like. For instance, yes, the same example means the same function. In this case, the function is your function is f z is equal to x square minus y square is plus 2 plus I into 2 x y. This is the transformation, this is the map w is the map. So, this is the x y plane and this is x y plane and this is u v. Okay, and this is the map from this plane to this plane is equal to w is equal to f z. Okay. Now, in the previous example, I took two curves. One curve, if you recall, one curve was something like this, and another one was this, and another one was this, right? Another one is this, and we saw that this angle was pi by 4, and we checked whether it is a pi by 4 or not. Now, you see this in this figure, there are randomly taken, suppose we have, if we take a grid here. Now, all these angles are 90 degree, all these angles are 90 degree. Okay. Now, the blue one, the transformation of blue one are this, these are the transformation of blue one. And the red one, which is the horizontal axis here, the transformation of horizontal axis are this transformation. Now, you see initially the angle was 90 degree, here also these angles are 90 degree, these angles are 90 degree. So, this is conformal mapping. So, if you take any arbitrary, now similarly you can take, you can further explore it or further do the similar exercise with different functions. As I say, there is a book by Churchill on complex variable. There are many other examples given, exercise problems are given where a map is given and you have to check, or you have to find out the angle and then check the angles are preserved or not. All different kinds of examples and exercises are given. You do that exercise and then you convince yourself whether how these angles are preserved. Now, that is fine, conformal mapping we discussed, but what we have to understand, what is the use of this conformal mapping in the context of elasticity problem. At this point, please note, this is the thing that we required for complex variable, and next subsequent classes what we do is we will apply this concept to formulate the elasticity problem and further solve them. But at this point, please note, we have discussed bare minimum thing that we require to formulate the elasticity problem. It is a very brief account of complex variable method. In order to get the detailed account, please go through book, and in order to get a comprehensive idea about the conformal mapping or different kinds of For instance, the unique-codifferent theorem that we discussed in the previous class, line integral, then path independent. In order to get the detail of all these concepts, in order to have better comprehension of all these concepts, you have to go through a book on complex variable. Okay. Now, with this, you see what is the use of this method, how it will be used in your previous classes. Okay. You see, now in the next in the subsequent classes, what we see, for instance, this is a conformal, this is how we define a conformal map. We have a xy plane, then we'll have another plane, and then this is a domain. See, R is the domain in xy plane, and then we define a map like this, z is equal to like this, and we use this map to be conformal. We use a conformal map so that the angle between these lines are preserved, angle between two lines are preserved. Now the use of this, you see, this is a very important problem, and if you recall, in one of the classes I gave a very brief idea about this problem. Now see, we have to find out the solution of this problem, and finding solution of this problem is just not an exercise. When we do this, we will discuss that in detail. The solution of this problem will be the motivation of our next week lectures. Now, we have to find out in that context, the solution, finding the solution of this problem is very, very important. The problem is, we have a plate which is subjected to in-plane loading, and the plate has an elliptical hole there, and then what we are interested in, what happens to the distribution of stresses, what is the expression of, how do we get the way we have the closed form solution of difference, the stress distribution and then displacement distribution. Similarly, we want the closed form relation of the distribution of stresses on this plane. Now, had it been a circular hole, we will be doing that one exercise of circular hole in the next class. Now, had it been circular hole, it would have been very easier, because you can the whole of the circle can be this, for instance, this circle can be represented, the entire surface can be represented by one parameter r, but in this case it is not as trivial as circle. What we do now is, we will define a map between this ellipse and a circle. Suppose we have a circle and we define a map between this circle and ellipse. This is the map between this circle and ellipse, and this map is a conformal map. The conformal mapping just now we discussed, this map will be a conformal mapping. And then once we have this mapping, then what we do is, we actually solve the problem on this space. But when we solve this, we introduce this map into this into the solution, into the formulation, so that we have to do the exercise on this, but since as this map is introduced here, final solution will be get of this problem. This exercise will be, this step will be clear when we actually implement this. Here on this slide, what I want to tell you, the point what I want to make is that the conformal mapping is important, and this map will be using to solve this problem. Next class, first we derive the equations for plane elasticity problem using through complex variable method without any conformal mapping, and then see how the complex variable method can be used to solve some elasticity problem. We will demonstrate through some examples, and then next class we will come to the conformal mapping. We will try to solve this example using conformal mapping concept. With this I stop today. See you in the next class. Thank you.